right. All right, I'm going to get started here. This time, I'm pretty sure we have started recording already, because I forgot last time. And the interesting part was that I actually had OBS already turned on, and I checked the volume. You guys cannot see it, but it's actually visible to me. I could actually double check and see everything, except I forgot the one last step, which is to click start streaming. And that has happened several times. I will set up everything and then just forget to push that button, like the last step. So it's good to remind me once in a while, just to check, okay, is it being recorded? Is the mic on? That would certainly be helpful. All right. So are there any questions about the program that we did on last Thursday? So I did some studying. I went home. I actually found out how variable number of parameters was actually processed in C and C++. So as it turns out, I was missing one thing of the convention. After the first argument, after the last declared argument, there's one hidden argument that specifies the number of other arguments behind it. So there's a counter behind that. So that was the one thing that I was missing on the other day. And that's why things seem to be offset a little bit between the first and the second argument. But there was one thing in between that was basically explaining that. Yes?
When you're incrementing the pointer, is it the same thing?
So when I'm incrementing the pointer, the second thing after the last declared argument is a hidden argument that specifies how many more arguments there are on the stack. But it doesn't tell you anything about the type either. All it says is there are this many things on the stack. But it doesn't tell you, what those things are, how much space it's taking. So it is still up to the subroutine itself to interpret it. So for the most part, I was 90% correct in terms of what I said, with the missing one counter in between. So that was the only thing that I was incorrect when I was talking about that topic. So other than that, do we have any other questions regarding how arguments are pushed on stack? No questions? Okay. So I thought about this for quite a bit, and I thought it would be a great idea to show you some mysterious programs that do not work. And if you had not taken this class and passed this class with at least a B or an A, you would not be able to explain why that program behaved the way that it did. And then after that, I can also do an example of hacking a program to show you what you can do, or what hackers can do, okay? Now, I'm not even an amateur hacker, so what I know about hacking is really, really small, okay? So if I can figure out these things, professional hackers certainly can figure out a lot more than what I would talk about in this class. So let's see if those things are going to kind of inspire some of you to look into cybersecurity, hacking, being a white hat. I'm hoping none of you get inspired by me to become a black hat. And if you do not tell people that you were inspired by me to become a black hat. Okay, so let's go ahead and write some programs. Okay, so we'll write some not so interesting programs at the beginning, and then it will start to get kind of like, whoa, what is that doing? Okay, so we'll take a look at the program1.c. Okay, so we have function f, doesn't do much, okay, and it returns, and function f has an array of local variables. Okay, so it has an integer array. Okay, nothing too fancy. And it's an array of one element. Okay, it doesn't really matter. Okay, and it's not doing anything with it yet. And then we have function g, which doesn't do a single thing. And then we have the usual, the main subroutine that in this case only calls function f, and then it returns to the caller, returns to the operating system. So this program at this point doesn't seem to be much. Okay, everybody knows what it is going to do, which is pretty much next to nothing. Right? It calls function f, function f has a local variable a, which is an array of one element, and each element is an integer. And because I'm using a 64-bit architecture, it is going to have a 64-bit integer by default. And then it's going to return, f is going to return back to main. Main is going to return, and basically nothing happens. Is that OK? All right. So what we'll do now is we'll run this program inside GDB. And before we run it in GDB, I'm going to insert one thing here, which doesn't seem to make any sense. OK? I'm initializing element 0 of a in f to 0. OK? I can initialize it to anything. It doesn't really matter, because nobody's going to use it. And nobody's going to even know about array a from outside of function f, because it's a local variable. Is that OK? So this all seems to be pretty useless. But I'm going to use this to give me a clue of how to hack this program so that it would do something that is really strange. OK? So we'll exit the editor. GCC-G-O. We can do a warn all, which it might complain about array A. I'm not sure. Oh, OK. Proc1. There we go. Yep. So it does complain about variable A is set but not used. But it's really just a warning, which makes sense, right? Because I put a value into a bracket 0, but I'm not using it anywhere else. So GCC is basically saying, well, if you put a value into a variable, you probably intend to use the variable somewhere else in the program. If I do not find that you use that variable elsewhere in the program, you might have a flaw in your program, okay? Or this is indicative that I might be missing something in the program. But in this case, I'm not missing anything, because I'm setting up this program to illustrate a concept. So then we go into GDB, proc1, put a breakpoint in f, and just run the program. Okay? Not surprisingly, it stops right at that statement. But at this point, I can print out certain things that are going to be very useful to me later on. Okay? So what I'll do is I'm going to print, first of all, the address of a bracket 0. Okay? Somewhere on the stack, which is what we expect. Local variables, parameters, those are all on the stack. Is that OK? I mean, that concept we have been talking about for, what, a week or 2 weeks already, maybe around that time. OK? So that is hardly surprising. But what I also want to find out is what else is on the stack. OK? First of all, I want to print where is main. The ampersand main tells me where is the entry point of the main subroutine. OK? That's a funny number, lots of 5s, and then 1, 3a. OK? So using this, I can now examine other things on the stack. I was trying to find the letter to mean 8 bytes, or 64-bit integers, but I couldn't remember what it was. Now I remember it's Q, which stands for quad word. Okay, one word is 2 bytes, and so quad word is 8 bytes. Okay, so it's Q. So I'm going to print like 8 Q, quad words, and display each one in hexadecimal on the stack. No, oh, OK, it needs to tell me where I should print. So I'm going to use a bracket 0. So it's showing me, those are not 8-byte things. So if I cannot remember, I'm going to re-examine how to display something that is 8 bytes long. So we got byte, half word, word, giant. OK, G, there we go. OK, so we're displaying some content on the stack right now. And it starts with a bracket 0. So the first item we see here is a bracket 0. Okay? It has some initialized value because I have not executed the assignment statement. So if I single step and execute the assignment statement and print this again, that location would become zeros. So only this half is becoming 0 because integers are 32-bit wide and not 64-bit wide. So int itself is only 32-bit wide. If I use int 64_t, then it would be 64-bit wide. So I did not, I made the wrong assumption there. OK, but that's OK. It's not a big problem. So now we have a few other things on the stack, right? We got a few other things on the stack. And what I want to find out is, Do you think you can find the return address somewhere here? Where do you think is the return address? Where is f supposed to be returning to? It's supposed to return to main, okay? So where is main? Okay, that has scrolled off the screen already, so I'm going to redisplay where main is. Main is a whole bunch of 5s and then 1, 3a. So let's count the number of digits here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But in order to make 64 bits, we're supposed to have 16 digits, right? So we have how many implicit zeros on the left-hand side? We have 4, okay? So very good. So do we see anything here that seems to resemble a return address to main? We can actually see the address of main here, right? A good portion of it. And the way the things are displayed is kind of misleading because they're off a little bit. So let me see if I can make it look a little bit nicer like that. I think they are now aligned much better, so that's good. Okay, so we'll look at it this way. So which one do you think is the return address? Okay, well, we'll look at each one one by one. Okay, does this look like a return address to you? Does it resemble the main address? Nope. What about the next one? Does it resemble the main address? Yeah, it does. It's basically, we can count the number of bytes away, right? So we have to subtract 3a from 48. That would be, it's less than 16 bytes. I mean, it's actually pretty close because from 3a to 40 is how many? A is 10, so how much do we have to add to 10 to get to 16? 6, okay? And 6 plus 8 is only 14. In other words, this is only 14 bytes away from the beginning of main, which seems pretty reasonable to me. I need a few bytes to set up the call, set up the, whatever the stack needs to set up to make the call to the subroutine. So I think this is our return address. Is that okay? Are we doing okay so far with what I perceive as the return address? Okay, pretty sure about it. So now the question is, well, it's the return address. Do you think if I, quote unquote, accidentally do some bad coding in F, okay, do you think I can maybe accidentally modify that address? Yeah. Well, let's figure out where it is first, okay? So the way we figure out where it is to look at the bytes here, and you can see how each row is using 16 bytes. So the way we count the bytes is a little bit funny. This is 60, right? This is 60, 61, 62, 63, and so on. Why do we count that way? Because the Intel processor is what we call a little Endian processor. A little Endian processor means when you have an integer that requires multiple bytes to represent it, the least significant byte is sitting at the lowest address location. Let me say that one more time, okay? Little Endian, E-N-D-I-A-N, okay, means a processor architecture when it stores a multi-byte integer, the least significant byte is at the lowest address. This 70 is the lowest byte of this entire 64-bit number, and therefore it is sitting at the lowest address. And this entire row starts at location 60. So 60 is corresponding to the 70. So when we get here, this portion, which is the portion that I'm really interested in, is going to be starting at location 68. Does that make sense? Because the entire row has 16 bytes, one half is going to the first number, and the other half is going to the second number. But the number that I'm interested in is I'm changing this byte here. I want to move this byte to somewhere else. Where do I want to move it to? Well, what about the address of G? So now I say, where is G as a subroutine? G as a subroutine starts at location 133, okay? Which is kind of making sense because main is 13A, right? G has basically nothing except for a return, and it's at location 133. Yeah, kind of makes sense. So now I want to look into the possibility of what do I need to do to change these bytes here into G. In other words, all I really need is to change the 148 to the 133. What kind of bad programming practice do I need to do to quote unquote accidentally make that change? What do you think? I'm looking for an alias. I'm looking for a way to refer to this particular 32-bit integer, 1, 2, 3, 4, 5, 6, 7, 8. I'm looking for a way to refer to these 8 bytes, and so that I can do some calculations and change that 48 into a 33. Yes, go ahead. Access past the end of the array. Very good. Okay. So that means, now I want to look into things not as a giant anymore. Okay, I cannot remember the commands of X, so I have to look it up. So this time I'm looking into a 32-bit thing, which is a word. Okay, a W is 32-bit wide. I still want to display as in hexadecimal. And where is array A again? Where is array A? So array A is at location E5C. And we can now also look at the size of each thing inside the array. So we can say size of A bracket 0, and it is 4. So this confirms that we are dealing with 32-bit integer when we only declare int. Okay, so now I'm going to ask you a question. A bracket what is going to refer to these bytes over here? 168 is the address of the lowest location of what is highlighted on screen at this point. And then at the bottom, the address of A, the address of A is ending with 15C. So, okay, let me see if I can print both at the same time. So just give me a second here. We'll display this, and then we'll display, oops, I think I just got past it. Nope. It's a W. Oh, okay. Oh, that's, okay. There we go. Okay. So based on this information, where do you think, if I say a print in hexadecimal, A bracket, and you guys can help me figure out this question mark, what do you think I need to specify in place of the question mark to end up with this pattern here? That is the question. This is 168, right? The beginning of the entire array is at 15C. So what is the difference in terms of, just in terms of bytes? It's not that much of difference. Come on, you guys can figure this out. What is 168 in hexadecimal minus 15C in hexadecimal? Yep.
Isn't that 148? It's not 168.
It's 168 here, because 160 refers to this byte. 168 will now will refer to this byte, which is what I need to address. So I need this byte and the other 3 bytes that are to its that are higher addresses. But this is the starting point. I'm only concerned about the starting point here. Okay. So if you guys cannot remember how to do hexadecimal subtraction, we can ask the debugger to do it for us, okay? So we can say print in hexadecimal. That part is not really that important. And we say what is 168 minus in hexadecimal 15C? And the answer is C, which is 12, right? So if it is 12 bytes away from the beginning of the array A, what would be the index if I were to look at this as an element of the array, which it is not, right? It will be 3, exactly, because 12 divided by 4 is 3. So let's double check that theory. So we say print /x, which means you print in hexadecimal, a bracket 3. And then most of you will now say, but a only has one element. A bracket 0 is the only element of A. Well, let me ask you again. In C and C++, is there anything that will prevent me from pretending that the array has more elements than it actually has? There's nothing standing in my way. Guess what we do? Guess what we get? We get that, right? Then you go like, well, but tech, it's pretty unlikely that your program will specify exactly that value. That is really unlikely. But my program may do some calculations with the cell values, right? With the element value in an array, adding something to it, subtracting something from it, making small changes, right? So now we can look at what it is now and what we want it to be. So what we want it to be, this time I'm not going to use /x because I want to use the decimal number in my program. So now this time we look at 0x148, which is what it is, minus what we want it to be, which is the last 3 digits of G. So which is 133, I think. It's only off by 21. If I subtract 21 from a bracket 3, the program will do something that's wonky. Is that okay? Yep.
Going back a little bit, can you explain again how you count, figure out where you are, 0, where you go from 0 to, where you start counting at 0?
Okay, I understand your question. So, okay, so what we want to do is to look at the addresses. We look at the address of the first element of A, right? 15C. We look at the address of the next element of A. It's at 160. We look at the next one. It is at A bracket 2 is at 164. And then the next one is at location 168. Because they're 4 off from each other, because each element of the array has 4 bytes. So when you are computing the address of different elements of the array, all you're really doing is multiplying the index by the size of each element of the array and add that much to the beginning of the entire array, and that's how you calculate the address of individual elements of an array. Is that okay? That part is kind of implied in C and C++ in your cisp310 class, because when you add 1 to a pointer, the address of the pointer, or the calculated address, will be the address of the next element compared to what you're pointing at. So that part is kind of implied already in C and C++ if your professor had time to talk about pointers, or at least pointer arithmetics in this case. Is that okay? Yep.
If you're doing the counting up like that, how come when you show the hexadecimal numbers above, you have 2 columns worth of numbers?
It's because I'm considering I'm asking the program to print things in quote-unquote giant mode, which means it is taking 64 bits or 8 bytes and look at those 8 bytes as if it is one single 64-bit integer. So each row has 16 bytes, but since each integer is taking 8 bytes, and that's why there are only 2 columns per row. Yep. So those are all very good questions, but now I get my magic number, which is 21, which is coincidentally half of 42. So maybe 42 is special after all. Okay, so now I got what I want. I'm going to go back to my program, make a very simple change to this. And we want to find out what the program is going to do. Well, you guys already know what the program is going to do because I have been working pretty hard to get the program to do one wonky thing, right? So what do you think this program is going to do? It won't blow up. That's the problem. If it were to blow up, it's like, okay, good. We got some memory corruption problem, and we know how to fix that. Okay, we know there's a problem. Except this is not going to blow up, or not immediately. Okay, the first symptom is something that you would not be able to explain without the knowledge that you gain in this class. Well, hopefully that you would have gained in this class. Do you guys want to Look at the program, how it's going to crash, okay? Now, it might be off a little bit, so because, these numbers can be still off, because I changed the program already, and that alone is going to change some of the offsets, so that might change already. So I might need to do some additional adjustments to get the program to crash or misbehave the way that I want it to misbehave. So put a breakpoint on F again, run the program, and I just want to double check here, okay, single step, and I want to print just like what we did before, or examine. Well, let's put 16 objects here. Each one is a word in hexadecimal, and we want to print things that are right after the array A here. So we can see, so the way we read this is going to be really kind of funny. So let's do it in a slightly different way here. We'll do it the same way as we did last time, which is this one here. So the return address is now changed to 129 because I made some changes earlier. And should we subtract? Yeah, we should subtract. And when we print the address of G, it is a 135. So we have to add not 6, right? Because these are all in hexadecimal. Because my objective is to make this number 135. So 129 is 7 bytes away from rolling over. So 7 plus 3, 5 is 12. So I need to add 12 back to that number. Okay. So let me tweak it one more time. So that would be 21. Run the program, put a breakpoint on function f again, run the program, single step, print, examine 16 giant in hexadecimal, starting with the address of A bracket 1. We got 135, very good. Print the address of G. It is still at 135, so the program is going to misbehave now, which is what we want, okay? So let me go back out again, go back in again, okay? Put a breakpoint on F, put a breakpoint on F, and then we'll put a breakpoint on G, and then run the program, okay? We are now in F. If I single step, it's going to make some changes to A bracket 3, which is an element that does not exist, right? But let's say you didn't catch this, and you single step one more time. We're now at the end of function F. Where do you think function f will return to? It returns to G, not main, okay? Now, just to confirm that is the case, single step, and we're now in G. You can see from the feedback of the debugger, we're now in G on line 10, not in main anymore. We're not in Kansas anymore. So, okay. So do we see the problem? Do we see what the program is doing here? It's not crashing. It is returning to a subroutine that you never called anywhere in your code. Yes, go ahead.
Wouldn't the compiler catch the size of the array to be outside the boundaries?
Nope. C, the compiler cannot make any assumptions because. All right. Well, even if that is the case, even if the compiler knows that, you can access something out of bound in a subroutine. In other words, you can pass A to another subroutine and then access A out of bound in the other subroutine. So there's no way to actually address the core issue of being able to use a pointer and treat it as an array. That is the core issue in C and C++, which also makes it kind of really useful, but at the same time, it is also very bad. Okay, so does everybody can everybody see what the problem is when I ran this program? Okay, I'll do it one more time and explain it. Okay, we run it. Main calls f. F has got one statement to do, but when f returns, it is returning to line 10, which is the first line in F. But we never called F anywhere in this program. Oh, G, sorry, yeah. So F returns to G, which we never called anywhere within this program. So if you did not know about stack corruption and the return address is on the stack, and this kind of thing can happen, what if this happened in CISP360, which you should have taken? How would you explain this? You wouldn't be able to. Huh? But it can also lead to other kinds of problems too. All kinds of other issues can happen when you access an array out of bound in a C or C++ program. Because you'll be modifying things that you should not be modifying on the stack. Is that okay? But this particularly is difficult to debug, because when you use a debugger, I don't really care whether you use GDB or whether you use printfs or couts to debug your program. The behavior is going to be the same. You call a subroutine, when it returns, it's returning to a subroutine that you never called or not in that spot. And then you wouldn't be able to explain it because, well, I mean, this is not a concept that we talked about in CISP360. How many people knew there was a stack that stores return addresses and every local variable is living on the stack in CISP360? Okay? So you guys would know something about this, would think that it's possible? Maybe? Okay, so let's go back and look at the source code of the program, okay? Because I think it's kind of important to look back at the source code, because somebody can complain and go like, but Tech, you handpicked these values, okay, to make this program crashed or misbehave in this particular way. What are the chances that this actually would happen to a real life program? It's very likely. Okay? Except in a real life program, you'll be looking at thousands and thousands and thousands of lines of code and not know where to focus. In other words, this could happen to a real life program if you're not careful, except in the case of a real life program, it will be much harder for you to find out where did I access an array out of bound, because you have thousands of lines of code to go over. Is that okay? Do we have any questions about how this program was handcrafted so that when F returns, instead of returning back to main, it returns to G? No questions? So we are good with this program? Okay? Yes, go ahead.
You intentionally knew where G was.
Mm-hmm.
Change it. Okay, but normally, if you go out of bounds, it would just crash. It would go any.
Nope. No, not in this case.
I mean,
If you're
yes, it would go back to G, but in normal, it would, if you
not necessarily, it all depends on how you modify the locations, right? So if this program had like 600 lines of code, okay, and this is actually a real calculation, not 21, which is a handcrafted value, right? So you're minus equal to and then some particular value as a difference, okay? The chances that that new address is a place somewhere in your program is pretty high. So instead of landing square in the middle at the beginning of G, you'll be landing somewhere else. But the chances of it actually landing legitimately into some place where you actually have code in the program is still really high. Do you see the point? So you still won't be returning back to where you're supposed to be, and yet the program is not crashing, and that makes debugging extremely difficult because it's not crashing. If your program is not crashing, when are you going to notice that something has gone wrong? Until you see the result, or by the time it crashes, it's already way past where the problem was. Okay? For instance, this program does crash, okay? Because after G, when G returns, then G has the wrong place to return to, and the program will crash. But then you'll be asking the question, why is G crashing? I never called G. And you will never put your focus on F ever in the case of debugging this program. Is that okay? All right. So do we have any other questions about this program, which the only purpose of this program is to illustrate one little thing in your C++ program can lead to a symptom that is very difficult to diagnose and to figure out in your previous class. Now that you know about this class and you know what kind of stuff is on the stack and what modifications on stacks, items can do, then next time your program crashes, quote unquote, mysteriously, your first suspicion is, I might have messed up the stack. Yep.
One last question.
Yes.
If C compilers and C++ compilers know about this issue, where does it get fixed?
How would you fix it?
You basically, you look at the size of the array and make sure you're within the boundary.
Well, let me ask you this question then. What if I have another function, we'll call it gh here, okay? H takes a pointer to an integer, we call it p as a pointer, and it says, p plus 3 minus equal 21. And instead here, we say HA. Then you cannot pass the size anymore. The size of the array is not passed. Because when you pass an array in C and C++, you're only passing the beginning of the array. You're not passing, there's no size of the array that is being passed. So you still end up with the same problem. Except, hey, now the problem is even further away from, the symptom is going to display. So are we good so far with this? We good? All right. So I'm not going to ask you to design a program in the final exam to crash in a very specific way. Okay, that's not in the scope of this class. Okay, if you fully understand what I'm trying to illustrate here and understand the mechanism, then you're doing good in this class. Okay, you're understanding the concepts, you're understanding what is on the stack, what is the return address, where is the return address, what local variables are, how do we do array indexing, and all of those mechanisms that we just talked about. If you kind of have a general idea of what this is, how it's happening, but the details might need some time to look up and to restudy, you're still doing okay, because it's the concept that is important. Exactly how I found 21 or exactly how I found the 3, that's a little bit mechanical, that's kind of like pine needle stuff. But if you focus on the tree and you still understand the pine tree, I would say that's good, On the other hand, if somebody looks at this and go like, I have no idea what this program is trying to illustrate, then we have either some heavy-duty studying to do, or this class may actually be revealing a truth that that person may not have known before. And I'm going to not mention what that truth is going to be. But I think it is fair to say that if this were to happen in a regular program in cisp360, most people would not be able to figure it out or to explain it. So what was the explanation in cisp360 when somebody mentioned, well, what if we access an array out of bound? What would be the answer in that class? The program will crash, okay? It'll be garbage. It'll be accessing some location that is not a part of the array. But will it crash? Well, maybe, maybe not. Not necessarily, exactly. If it crashes all the time at that spot, you're actually in luck. Because, because the symptom of the problem is exactly where the problem is. But this is not the case. The symptom is way past the cause of the problem. Yep.
For example, if we have like 1,000 lines of code, should we basically trace when the function is called, the address when the function is called, and the address of the
It's hard because sometimes the subroutine that's actually doing the damage, like in this case, function h, has no idea where the pointer is, right? H is just saying, hey, my caller is giving me this pointer and asks me to subtract 21 from where P is pointing to, where 3 locations past P is pointing to. It's like, okay, I can do that, but I don't know what I'm doing. I don't know whose array I'm accessing and whether that array actually has that location legitimately, have that location as an element. I have no idea, but if I'm told to do it, I'll do it. So what? Yes, go ahead.
So inside the function h,
Yeah, I think I made a mistake here.
oh,
Yeah, so function h should be p. I need parentheses around these two, and then do a minus equal to 21. Yep. But the idea is the same. I'm deferring it to a subroutine to do the damage. I'm hiring a hitman. And therefore H. H for hitman. So are we good so far? Sort of? Okay, so based on this, I'm going to show you how to hack a program, okay? It is all related to this class, okay? And this is actually from GCC. It is not the TTP. It's not text toy processor. It's not text homebrew assembler. It's not text on tool. This is legitimately plain GCC, okay? So the next program I'm going to work on is actually on the class site. So let me get into the class site first. And or maybe not. Well, maybe it's in this section here somewhere. Nope, it's not there. Okay. We'll look into a past semester then. It's possible it's in an earlier semester. Let's look in, not lab. Go back. Lecture. Nope, it's not there either. Oh, man. I usually put it at the beginning over here. And it's not there. Caller, callee. Nope. I cannot find it. But I wrote a program, and compiled in GCC, and it has a password protection feature, to access a certain portion of the program. And that was a program that I used to illustrate, how to, crash a program in a certain way. And then from the evidence that you're gathering, when you crash the program, you can figure out how to crack the program and bypass the password checking, section. But I don't remember where I put that program. So I may not be able to work on that today. So maybe next time. I'll spend just a little bit more time to find it. And if I can't find it, I will do it next time. So it'll be in shared for sure. Huh? Yeah, but I can't remember how I called it either. Let's see, decompiled is, nope, not one of those. Okay, maybe Maybe next time. I'll show you the program next time. Okay, so that means I'm going to shift gear and talk about tonight's lab. So we don't have a whole lot of labs left. So what we'll do tonight is to deal with recursive calls. So we're going to get into recursion. If we look into, okay, so we'll do a preview first. Okay, we'll do a quick preview so that you have a little bit of idea of what the questions are about. Question number 1, when a function returns a scalar type, what is the mechanism in the context of this class? I'm not going to give you the answer, and please do not read out the correct answer, because I know many of you know the answer already, okay? So that's nothing new, right? This is like old stuff. Next question. How are parameters passed from the caller to a subroutine? Okay, so I'm going to read out the choices, but I'm not going to give you the right answer. In registers A, B, and possibly C, in special parameter registers, such as the instruction register, on the stack below the return address, none of the other answers is correct, or on the stack above or higher address than the return address. So I'm going to leave it up to you guys to figure out which answer is correct. In fact, I'm going to work on a sample program, okay, that will probably answer many of these questions already. Next, okay, the following C program, the following is the C code you need to implement for this lab. So for those of you who are not familiar, this is the ternary operator. It's really the same thing as if n is less than 2, return n, otherwise return f of n minus 1 plus f of n minus 2. Wait, that looks vaguely familiar, especially if you have taken CISP 440 or 430. What is that? Huh? No. It's a pretty important concept, recursive concept, or example of recursion in computer science. But it doesn't have to be computed recursively, but most people do. It's a good example. What is it? It starts with F. Fibonacci. It's Fibonacci. This is how we can define Fibonacci recursively. Okay? So the main function can be assumed to be like this. We have a local variable x. We call Fibonacci with whatever number you want to test it with, and then it returns a 0. So obviously, the question mark is representing a value that you're going to use to test the algorithm. The question is function f recursive? I'm not going to answer that question. Okay, even if you have no idea what recursion is, you probably should know the answer to that one already. So question number 4 is asking you to actually implement the code and implement it in TTP-ASM. So from here on, remember, TTP-ASM refers to the source code that you're going to write, and the code is going to run in LogicSim. Okay, so that's the source code. It is not the comma-separated value file. It is what you paste into the source tab of the assembler. Okay, so you're going to have to implement that subroutine for this particular homework assignment. It is not going to be due in one lapse time. As usual, you have 1 week to work on it. Okay, so don't push yourself, try to rush it. Just really try to understand the concepts first before you give this program a try. So this is the only part that is going to take you any amount of time to answer, right? I mean, the first 3 questions, I think most of you kind of know the answers already. It's only this part that's going to be a little bit time consuming. Are we doing okay so far? Do we have a quick understanding of what we're going to do for this lab? Okay. So what I'll do is I'm going to give you some examples so that you have an idea of how to get started with it. I have a few examples that we can use. Oh, by the way, talking about Fibonacci, this is not political, it is just funny, okay? So I make a disclaimer first. If you look at Fibonacci and Trump, I think there's a picture that correlates the two. There's a relationship between the two. Somebody fit the Fibonacci curve into a side profile picture of Trump, and it fits perfectly. It does. As I said, it's not a political statement. It's just, some really kind of weird coincidence. All right. Okay. So we're going to write a subroutine that is recursive. And, we can do this. It's called the Tower of Hanoi. Yeah, let's do Tower of Hanoi. Okay. So this is the Tower of Hanoi. It has 3 arguments. It has argument A, argument B. Okay, I'll name these correctly. So we have from, we have to, and then we have via. Okay. So the Tower of Hanoi is given to you as a problem. Okay, there are 3 poles. Okay, the first pole is named from, the second pole is named to, and then the second pole is via, and then the third pole is named to. Okay, so the idea is I will give you a number of disks on the first pole, and your job is to move all of those disks from the first pole to the last pole, which is the to pole. Okay? But the idea is you cannot have a bigger disk sitting on top of a smaller disk. And you can only move one disk at a time. So the question is, how do you do it? So I'm going to show you a pictorial representation first and give you a kind of pictorial answer to a simple case. Then we'll work on the actual algorithm. So in this class, I will give you the algorithm. You don't have to come up with the algorithm. You just have to understand what it is and how it is implemented in assembly. Okay? So that's going to be the focus of this class. So let me get Zerno up. And I think control equal to. Yep. Okay. All right. So you have 3 poles, 1, 2, 3. This is from, this is via, and this is to. So when we are looking at those parameters, we are really only looking at 0, 1, and 2. Okay, we're just looking at a number that uniquely identifies the poles. So we'll just call this pole 0. This is pole 1, and this is pole 2. I think I'm missing one argument, which is n, the number of disks to move. So we'll go back and fix that first. So we have n here. Okay. So I'll ask you one question. These poles are empty at this point. What if I have one disk to move? So I have one disk to move from the from pole, which is pole 0, to pole 2. Okay. What should I do? Just move it, easy peasy, because if you only have one disk, then you don't have to worry at all that you might be putting a bigger disk on top of a smaller disk. So that restriction really does not do anything to you, so you might as well we'll just move it. Okay, what if you have 2 disks? In other words, what if we have 2 disks on pole 0, and your job is to move both disks from pole 0 to pole 2 eventually, but you are not allowed to put a bigger disk on top of a smaller disk. You can make use of pole 1 if that is going to be helpful to you. So what should we do? Move the smaller disk to pole 1, move the larger disk to pole 2, and then move the smaller disk from pole 1 back to pole 2. Does that make sense? Okay. So now let me ask you another question. What if I have n disks? So this portion is now representing n minus 1 disks, and this is only 1 disk here. What should I do? You guys figure out the last problem. You should be able to figure out this one. Yep. Oh, I thought you had an answer. The same thing. Exactly. So what you do is you say, I'm going to move n minus 1 disks from the from pole 0 to pole 1. Then I'm going to move the largest disk from pole 0 to pole 2. Then I'll move n minus 1 disks from pole 1 to pole 2. Then you go like, wait, but there are n minus 1 disks here, and we guarantee the n is at least 2 or 3 or whatever number, so it's not going to be easy to move it. So who knows how to move a bunch of disks from one pole to another pole? The same subroutine that you're writing. Okay? So what do we need to do? Recursively call that subroutine. So that's the idea of the recursive approach of solving problems like this. Okay? You're given a big problem with n disks. Okay? You break it down into smaller problems that only involve disks of one disk or n minus 1 disks. Well, what if it is what if it's n minus 1? Call the subroutine again. It will figure it out. Is that okay? So the implementation of the subroutine in C is like this. Okay, so I'll give you this code. You don't have to figure out recursive code in this class. So the base case is, what if n is 1? Well, if n is 1, it's easy, right? There's really nothing to do because we are not programming a robotic system, so I can't really actually do anything to move that disk. So I can only comment here to say that moving from pole to the 2 pole directly. Because if you only have one disk, you can do that. Is that okay? That stops the recursion. So the else case is saying, what if n does not equal to 1? Okay? And we'll just make the assumption that these are all unsigned integers. So we don't have to worry about negative values and stuff like that. So what if n is 2 or more? Well, then we do it recursively. So we basically call the Tower of Hanoi problem. And just like in the picture, okay, so we want to look at the picture first. So you have a subproblem now. The subproblem is, I got n minus 1 disks that I want to move from the from pole to the via pole using the 2 pole. Okay, so I'm only switching the arguments a little bit to make that call. So this will be going from the from pole to the via pole using the 2 pole, and the number of disks that I'm moving is n minus 1. Then we have the one thing that we have to move. Okay, so whether you want to do this one recursively or not is not important, because it is basically the end of the recursion. We only got one disk to move. And then after that, if you look back into the picture, now we have n minus 1 disks sitting on pole 1. We need to move those using pole 0 and then end up on pole 2. So the recursive call is going to be Hanoi via, from via to the 2 pole using the from pole, and there are n minus 1 of those. And that's it. That's the algorithm for Tower of Hanoi. Do we have any questions about this? Well, first of all, does it look recursive to you? Okay. Does it look sufficiently recursive to you? Because most of you know that factorial can be expressed recursively. That one is boring. This one is not. What if you say, yeah, but before I implement or understand anything, I want to see it happening? Okay. What do you do? What is your best friend in case of, I want to find out what is an animation of Tower of Hanoi in action? Google. Tower of Hanoi animation. And here we have a whole bunch. Okay, well, we'll look at this one. Is it long? Yeah, that's pretty long. And it shows you the call tree too. Okay, so it shows you the call tree. The arrangement of the arguments is a little bit different, but you get the same idea. Okay. And let me see if I can jump to just the animation part. Yep, I can. There we go. I'm impatient. This is how I watch movies too. And it's a very slow animation. But you saw the result of moving the top two disks from A to B first, right? And then the bottom one from A to C right away. And now we're moving the two disks from B to C, even though it's not directly, but the end result is that. Are we good? So the historical part of the Tower of Hanoi there's a temple somewhere, and the monks are supposed to solve this problem, except they have 64 disks instead of 2 or 3. So they have 64 disks. And the legend is when they solve that problem, that would mark the end of time, I guess. Okay, something really bad is going to happen. So I calculated the amount of time it takes to solve that problem, and I accelerated the time because I'm assuming that they can move one disk per second. Okay, 24/7, 365. We'll have a team of monks lined up to do it, right? So even if you assume 1 second per disk, it will take some billions of years to solve that problem. And that's after the sun is going to expand and engulf the earth in a big, huge fireball. So I thought, hey, that's not going to be a problem. Those monks will still be working on those things inside some kind of protective dome, so that they don't get killed by the sun's expansion and all that heat getting to Earth. So I'm not too concerned about that prediction that when Tower of Hanoi is solved, it is the end of time. Okay. So now we look back into the code, okay, and we ask, how do we implement this? What do you think? What is the most difficult part of implementing this program? No, there's a whole bunch of copy and pasting. So what we'll do is we're going to work on this, right? I mean, that's the whole idea of the rest of today's class, is to work on this so that you have an idea of how to do recursive call. So I can almost tell you with certainty that what you're looking at with this problem, it's far more complex than the Fibonacci problem. Okay, this is a lot more complex. It's just a little nastier than the other problem. So if we know how to solve this problem, we'll know how to solve the other problem. Okay. All right. So first thing first, Hanoi is the entry point of the subroutine. Okay. And this time I'm going to use a really cool feature of the assembler that I have not introduced to this class before. It is the ability to define labels to exact values, specific values that you want. Okay. In other words, you can define a label as a constant in C and C++, okay, which is kind of handy so that you don't have to deal with literal numbers. You can just refer to a symbolic name. Okay. So the first thing we want to do is to look at the stack. Okay. So by the time we get to the Hanoi entry point, what is going to be on the stack is n is going to be at the highest place because it's the last parameter, and then we have via, and then we have to, and then we have from. Okay. And then we have the return address on the stack. Is that okay? Does that look like something that we have learned in the previous week or so? Okay. So now you can say, oh, so that means the stack pointer is always pointing to the return address. 1 byte after that is from, 2 bytes after that is to, 3 bytes after that is via, and then 4 bytes after that is n. But when you're coding, remembering which one is which one, which number is which parameter, is kind of tedious. Okay, you may not want to do that. So instead of doing that, we now make use of another feature of the assembler, which is basically saying, oh, if you want return address to be 0, you can define it. So if you put a number or any expression, well, I shouldn't say any expression, if you put an expression that is in RPN or reverse Polish notation, otherwise known as postfix notation, it will calculate that expression and make the symbol equal to that particular value. Okay, we're not going to make use of that feature. Okay, so I want to avoid that kind of confusion. So we'll just use numbers. Okay, from is 1, 2 is 2, and then via is 3, and then n is 4. Is that okay? So I'm just defining a bunch of constants, so I don't have to constantly reminding myself, oh, which one is 1, which one is 2. Okay, we just refer to the symbols. Okay. So the first thing we need to do is to check whether n is 1 or not. So we are looking at this code here, whether n is 1. Okay, so we have to get to the address of parameter n, right? Because before we get to the value, we have to get to the address and then dereference it. Okay, so we basically use the old trick, LDI. Use any register other than D. Okay, you can use register A, B, or C. I'm going to use register A here. So I load A with n, add AD, because I want to add the stack pointer to A, so that A will now be the address of n. Okay, so A is now the address of parameter n. Is that what I really want to compare to 1, the address of n? I want the value of n, right? So how do I get to the value of n? Which instruction should I use? Which instruction gives you the ability to read from memory? That instruction also has the same symbol as one of the pins of the RAM component. Load LD. So LDA A. So now A is actually the value of parameter n. And then we have to compare that to 1. There's no easy way to do this, so we're going to LDI B with 1, CMP AB, and JZI to, well, according to this code, that's the then portion. JMPI to the else portion. This is the then portion. And the then portion really has nothing to do. So if you really want to do something here, to kind of signify that, yep, we are here, we're moving something, you can probably put in a bunch of no-op instruction or something special, just to remind yourself that this is representing the actual moving of the disks. But otherwise, it's not really doing anything significant. Okay. So now we have the else portion. The else portion looks awful. We have to call Hanoi 3 times. The first thing we have to push is n minus 1. So how do I get to n minus 1 at this point? If I'm trying to be as lazy as possible, how do I get to n minus 1? Is n already computed? Do I know the value of n at this point? I just compared it, right? So where is it now? It's in register A. Okay, so we'll make a note here. A already has n, okay? Because I want to kind of keep track of that. Okay, so if A is already in n, I can just do a decrement A, right? So A is now n minus 1. We push it on the stack, which is decrement D, and then STDA, okay? So this is how we push n minus 1 on the stack. Then we have to push 2 on the stack, right? How do we do that? Now this is going to be a little bit tricky, okay? Because we can use the same trick, okay? LDI A with the parameter 2, add AD, and then do a LDAA. Oops. AA, and then we can push it on the stack, right? Well, something is not right here. Because we have already pushed one extra item on the stack, the offset to the parameters are no longer what we computed earlier using those symbols. They're off by a little bit now. They're off by 1 byte. So that means you have to account for that. So you have to say, oh, it's not just 2, it is 2 plus 1. But wait, 2 plus 1 is an infix notation because the operator is between the values that it is supposed to operate on. That's not going to work. You have to use postfix, which is 2, 1 plus. You specify the operator at the end. Welcome to Japanese. No, I really don't know. I don't speak Japanese. But I know they changed the ordering of words compared to most languages. Okay, but this is postfix notation. Okay, well, that would push, okay, so this is pushing the parameter 2 on the stack. What else do we need to push? Well, the next one is via. So this is where the copying and pasting comes in. But every time you copy and paste, you have to be super careful because you have to remember to modify everything that you're supposed to modify, right? So in this case, it is not 2, it is via. And it is not 1 anymore, it is 2. Because we got 2 extra things sitting on the stack now. The stack pointer is no longer pointing at the return address. It is now pointing 2 bytes below where the return address is. So all the offsets to the parameters on the stack are now off by 2 bytes. Is that okay?
Can you put a space where you copy?
Sure. That. So this one is pushing via. So remember to change everything, to reflect what it's doing. And the last one to push is from. And I think by now most of you know how to do that, because we just have to say from, change via to from. And now everything is off by 3 bytes. What 3 bytes are we talking about? N minus 1 is taking 1 byte. 2 is taking another byte on the stack. Via is taking yet another byte on the stack. Those 3 bytes are sitting below the return address, but the stack pointer at this point is pointing to via, so everything is 3 bytes off. Yes?
So does the postfix notation only apply to the second operand on those opcodes? So like 3 plus and then only for from, or can you do that for the first one too?
For the first one too.
For A?
No, A, you mean register A?
Yeah,
Register A cannot be an expression. It has to be a single letter, has to be a register.
So,
It's only when you have an I, when you have an immediate. Whatever is immediate can use the postfix notation.
So you're pushing from, right?
I'm pushing, yes, changing the, change this too. Yep, there we go. Very good. Can we jump now? I got all the parameters. What else do you need to push from the caller's perspective before you jump into the subroutine? The return address. Okay. So once again, I'm going to use this kind of expression now to specify the return address. The way we use to specify return address has one problem. Okay? That one problem that we have is, what if I use the wrong label? Well, that's going to mess up your program. Okay? And copy and paste doesn't work when you have to modify that label. So now we are going to use one other way to do this. Okay? I'm going to put question marks here. And this is the return address. We decrement D, stda, push the return address. And then we have the unconditional branch to the subroutine, which is Hanoi. Okay, there we go. So now the question is, how do I specify this question mark here? Well, fortunately, the assembler has the notation of where is the beginning of the LDI instruction. A dot in an expression in a postfix notation represents the address of the current opcode that is being assembled. Okay? Let me put an imaginary opcode here. So I'm going to put a no op here, because no op doesn't do anything. I can just return to the no op. What is the difference between the address of the no op on line 51 and the LDI instruction on line 47? How many bytes are between those two instructions? Well, let's do some counting. LDI takes 2 bytes. 1, 2. Decrement takes 1 byte. 3. Store takes 1 byte. 4. JMPI takes 2 instructions, what, 5, 6, I think, right? So there are 6 bytes between the LDI instruction and the address of what I want to specify in register A. So the most convenient way to specify that is load A with dot 6 plus. Dot represents where I am on line 47. I'm just adding 6 to the address of the LDI instruction. This will be computed by the assembler, and then that at runtime, that address will be stored in A. So it's kind of the same thing as what we did before, but we don't have to define an extra label and risk using the wrong label, in the previous approach. So I'm just going to do one quick counting again because I don't trust myself. 1, 2, 3, 4, 5, 6. Yep. So 6 bytes. That is correct. Okay. Are we good? After the call, after we return, what are we supposed to do after the subroutine returns? There's no return value. Hanoi is a void function. There's nothing to process. But what do we need to do? What is on the stack right now on line 51 after the subroutine returns? Huh? No. The arguments. The arguments are still on the stack. The return address is taken care of by the subroutine, but the arguments are the responsibility of the caller. And how many bytes do we have on the stack for the arguments? 4 bytes, okay? Each one is 1 byte, and we got 4 of those. So, the quick way to do this is you can increment D 4 times, that works too. But you can also do an LDIA with 4, and then just add DA here. So you're basically just adding 4 to D, and that would deallocate 4 bytes all at the same time. So are we good so far with how to call on line 9? How to call Hanoi on line 9? Is that good so far? Yes? Okay. What do you think the next one, line 10, is going to look like? We are running out of time. But what do you do with the rest of this program? We have just implemented only line 9. What I said earlier, copy, paste, and modify. Okay, so we'll make a mark here. Okay, we'll say this is the end of the first call, because it always helps to know where we're supposed to start and where we are supposed to end, right? So this is the beginning of the first call. So what we do is we take all of this stuff here, copy, and then paste. After you paste, obviously the first thing you do is to change first to second. And then we cannot just decrement A anymore, because we really don't know what A has at this point. So you cannot do this anymore. Instead, we do a LDI A with 1. Why? Because on line 10, that's what you're passing. You're passing 1 as the count, the number of disks that you want to move. So we just specify a 1 here. The second, or the second last argument is via. So we modify that. Oh, did I make a mistake? Nope, I'm good. So this is going to be via. And then we have 2. The structure of the stack is going to be exactly the same, so the offset that we have to put into it is going to be the same. I'm just, just have to change the comment to reflect what we're doing here. And then the third one is, instead of from, we still have from, so from is good. And the rest is the same. And we have just taken care of line 10. How do we take care of line 11? Copy, paste, and modify. But this time we have a little bit more, because we have lost track of n entirely now. So you have to recompute the address of n, get to n, subtract 1 from it, then push it on the stack. The rest pretty much the same stuff. Okay? So before I let you guys go to the lab, okay, is this program illustrating any new technique when it comes to how to push arguments on the stack, how to access arguments that are on the stack, how to return from a subroutine? I mean the returning part here is going to be down here. What do we do? LD, AD, increment D, JMPA, right? That's the typical way of returning. You can use register B, by the way, but since A has no particular role to play, might as well use A. But none of that has changed, has it? So that is telling you recursive call is no different from a normal call. It really is not different. Is that okay? Because I just want to illustrate that point. This program looks really complicated. The logic seems to be pretty complicated if you are not comfortable with recursive subroutines. But when it comes to implementation, if I give you the C code, the translation of calls into assembly is no different. If this is not Hanoi, okay? If this is Eiffel Tower, this is the Great Wall, give me one more landmark that looks kind of tall. Needle, Space Needle, okay? They're all different subroutines. Would that change the way you pass arguments? Would it change the way you clean up arguments after the subroutine returns? Nope, not at all. So I think recursive call is now demystified. I mean, really, I'm really hoping that if anyone had a kind of mystical view of recursion, it's like, I have no idea what is going on with recursion, I'm really hoping this example illustrates and go like, oh, it's just as boring as any other function call. Because it is. If you're bored, it's a good sign. Are we good so far? So is this helping you to kind of get an understanding of how to implement Fibonacci? Which is a little bit simpler, but also a little bit different, because with Fibonacci, you have to add the return values of the two calls. So you have to kind of think of a way not to lose the return value of the first call while you're performing the second call. Okay? And the hint word is stack. Is that okay? So before we go, I'm going to give you the passcode of this particular lab because some of you probably want to know it. So we go back to the lab, go to edit mode. This is where I can find the passcode. Fib, for Fibonacci, not for lying. And I'm going to change the date so that you guys can get started. I'll give you a week to work on this. So once again, if you cannot finish it in one lab, don't worry. We got at least 2 labs to work on this one. So the 30th, so it will be the 6th of May.